Hello, a couple of days ago I received this DC-CT current sensor. So today I'm going to talk briefly about how it works, and then I'm going to do a quick demonstration with this circuit that I have made quite a while ago, which is a ZVS, and I have attached a high current transformer to the end. So first off, I'll explain how the DC-CT works. So the DC-CT is a current transformer, and that's the CT part of the name. And what's special about it is that it can also measure DC. That's why it's called a DC-CT. They have achieved this using the Platiše Flux Sensor design, and there is basically a core and there is a winding which measures the change in magnetic flux, and there is also another winding which can turn on and off to allow or not allow the passage of magnetic flux. And doing this, they can measure the constant flux there is when there is a DC current passing. This sensor not only can measure DC, but can also measure high frequency AC. It can go over 500 kilohertz. It is also among the most accurate sensors, mostly for this design, and it is power efficient. It uses less power than the common zero flux sensors. Even though it uses less power, it still needs a bit more power than the Sirius alone can provide, so that's why there is the MCTS2 power supply for powering the DC-CT. So the DC-CT is connected to the power supply, and then the power supply is connected to the Sirius, and this allows the Sirius to measure the sensor, and the sensor is powered by the power supply. So here I will show the setup. Here we have the DC-CT, and we've got the high current transformer, which I quickly wound using some aluminum wire on this ferrite core, and then the ZVS, which is over here. So connecting the DC-CT is very simple. We can just pass it one of the wires inside of it, and then we can connect the wire for the power supply. I always like to screw in the connectors so that they don't fall off. And here we can see there is the blue status light, which is currently on, and now we can go to DEWESoft X. So here we have DEWESoft X. Here we select the DC-CT. We can leave the current range for 1000 amps, but it's probably wiser to drop it a little to get a more precise measurement. The sampling rate should be fine like this, and we can measure. So to test how much current passes in this transformer, I can just connect it to power, and then once it's connected with a screwdriver, I can just short the high current end. And if I press freeze on DEWESoft X, we can see that we have collected some data. So here is what we collected on DEWESoft X. We can see that the voltage remains relatively constant, although there is some noise, which probably comes from my not so high quality power supply. Zooming in, we can see that there is a near perfect sine wave, though again there is a tiny bit of noise on top. You can, for example, quickly measure the frequency like so, and it is at roughly 136 kilohertz, which is higher than I expected, given that I can hear a high-pitched sound coming off from the transformer, so it definitely must have some lower frequency components. We also can see that it's a near perfect sine wave with a peak of roughly 43.6 amps. 43.6 amps is enough to melt a paperclip, mostly at these high frequencies when the skin effect is very significant in iron because it's high magnetic permeability. But if you want to measure a higher current, we can just increase the voltage on the power supply, and this should give us much higher current. Okay, so zooming out, we can see that now there are roughly 70 amps, and the sine wave has basically the same shape as before. Near perfect sine wave. We can also see here that the current doesn't remain constant. Whilst here, for example, I must have disconnected abruptly the screwdriver, and we can see that the voltage fluctuates in interesting ways. You can also see that here the current does not stay constant, and it does a bit of back and forth, reaching up to 68 amps peak before going to a more constant 54 amps, and then this slowly rises until it reaches this part over here with some 72 amps. I think that this demo should demonstrate relatively briefly how the DC-CT can measure high bandwidth, and I cannot see how accurate it is because I don't have another instruments to measure this current. Then something else that we can measure now is we can disconnect the ZVS from the capacitor bank and put the DC-CT in between, so we can see how much current goes between the ZVS and the capacitors. I will bring the voltage back to 12 volts. Here, when I power it, we should see a more interesting shape in the waveform. My power supply says that it draws roughly 0.3 amps, so here we can see that it draws up to 8.5 amps peak in these capacitor wires, and this can show a bit how the ZVS can slightly multiply the current, kind of. Of course, it's just power going back and forth, it's not 100% efficient. Here you can see that it's very roughly triangular, and here there is some high frequency noise. If we want to see it better, we can increase the sample rate, see if we can get better results. The noise is still we don't really have a very high sample rate that is really high enough to measure this noise, but it seems to be at very roughly some 3 megahertz, whilst this kind of triangular wave at roughly 40 kilohertz. We can also see how the current waveform looks under a greater load. So I can short the transformer with the screwdriver again, and it seems as though we use roughly the same amount of peak power, so now it seems to be getting a bit closer to a square wave, at least in this part over here. Okay, now the last current measurement that I would like to do is see how much power we are sending into the ZVS. So I can just pass my power supply cable inside of the DC-CT. Now we can see how much power the circuit draws. My power supply seems to be drawing some. The power supply says that we are drawing 0.334 amps. So as you can see here, we reach up to 4 amps peak and roughly minus 3 amps on the bottom. And here again we have this kind of triangular shape. We should also be able to see that at the start there is a much higher peak, and we draw up to roughly 28 amps. And we can see that here it is very noisy, and then it becomes less noisy. We can see how this power consumption changes when a load is applied. So again, short it with screwdriver, and we can see that when I connect the screwdriver, the amplitude, the AC part of the power consumption seems to go down, but we have a much bigger DC component as the whole wave is shifted up. And here we can see that it is the voltage seems to have some quite random fluctuations whilst the screwdriver is being attached. Anyways, that's all for this video, so thank you for watching, and for now, bye.